Jussi Pakkanen from Finland. We'll talk about powers of simplicity using Python in the Meson build system. Please.
Thank you. Good morning. My name is Jussi Pakkanen, and I'm. Oh, sorry. Is this good? Okay. So, I'm from Finland. Here's my Twitter handle. For my day job, I work at this company called Rakettitiede, which means rocket science in Finnish. Sadly, we don't work on actual rockets. We're just an IT consulting company, but we do all sorts of cool stuff. The presentation here is not related to anything that we're doing at work. This is sort of my free time project, but my employer was kind enough to sponsor me to visit this conference. So let's talk about building software. How many people here are actually building software rather than just using Python, just running it directly? So using something like C or C++ or something like that. A few people. Okay, good. So the Meson build system is the main title of this talk, and in a very small nutshell, it is a build system and it supports many languages. And C and C++ are the ones that we support, have the best support. But we also support things like Rust and Fortran and Java and C# and all those other things. And we support all of the platforms that are relevant today. So there's Linux, OS X, Windows, iOS, and Android. And there is also a port for Solaris, which people are using. So we try to be as widely available as possible. And also, we try to scale to projects of many sizes. So tens of thousands of files is roughly the size of the Chromium browser. And that's like the biggest sort of thing that you would usually build on your own machine. And the goal is that we need to be able to scale to projects of that size. Then there's other projects which kind of like the Google internal ones, which have hundreds of thousands of files and hundreds of millions of lines of code. So we design our system so that it should be, there's nothing preventing it from scaling to those sizes, but we haven't actually tested it ourselves. And the thing about Meson is that it's optimized for programmer productivity. So the less time you spend dealing with your build system, the better off we all are. And the best build system that there could possibly be is the one where you don't have to do anything. It would just read your mind and build your stuff for you. But unfortunately, we're not there yet. It's implemented in Python 3 and only Python 3. There's nothing, no extensions or anything like that. And we have a very strict rule is that we're not allowed to use any dependency that is outside of the Python standard library. So if you have Python 3 running, then you can just use that and you can run Meson and build your stuff. And that's the only dependency you will need. Oh. So then there are people who are using it. One of the big users is systemd, and they transitioned this year. There's some talks in the other Linux Peter conference with Leonard Pottering and possibly other people as well. So they're using it, and they're pretty happy with it. And there's the GStreamer multimedia framework, which consists of hundreds of plugins, and they deal with all these kind of video files and video codecs and audio codecs and transcoding codecs and all that stuff. And it's a very big project. GNOME projects in particular, they've been starting to use it. GNOME Builder, GNOME Software, GTK, which is the widget toolkit. Their version 4, the next version that's going to come out, it only builds with Meson. And glib is the foundational C library that they're using, and they have Meson support as well. Then there's the PiterPy video editor, which is a full non-linear video editor, and it's written also in Python, and it's using the GStreamer libraries. So if you haven't looked in that, you should. It's pretty cool. Other things in the core stack, so the X graphical server and Wayland, which is the future of graphical servers now that Mir is no longer with us. And they haven't used, they're in a position, they're transitioning to it. But, and there's the Mesa 3D graphics stack, which is used all on Android and also on Windows and all sorts of things. And there's a transition ongoing for them to start using this as well. They currently have, I think, 4 build systems, but they're trying to get that to 1 or possibly 2. And on our website, we have a list of other projects that are using it. But the interesting question is, why are they using it? These are all existing projects, and they had their build system already, and they were happy with it, and they were using it, and they were productive. So why did they change? And there's an interesting analogy here, because if we go back to the year 2000 or something like that, then everyone was using Perl. All the core infrastructure thing was done in Perl, web services were done in Perl, and all the tooling was done in Perl, or at least most of it. And yet, nowadays, Perl is pretty much gone. Python has taken over all of it. So why is this the case? Like, there's all these snakes that you see outside for these different logos. They could be camels. We could all be Perl programmers, but we're not. So why is that? And if you think about it, the reason is fairly clear, is that Python is readable and it's understandable. And if you look at a piece of Python code, you have a fairly good understanding of what it does. But if you have a look at a random piece of Perl code, you can't tell the difference if it's actual code or it's just a cat walking on a keyboard. And it's just completely ununderstandable. But for Python, it's like it speaks to you in a way that Perl doesn't. And there are other reasons for why people have transitioned to Meson, and one of them is speed. And Python is usually not known for speed, but so here's the Debian build log for building the systemd package, all the versions. And here at the top, you can see the 2.23 is the one which was using their old build system, and 2.34 was the new one. And this is on MIPS architecture. And this is the interesting piece. So the build used to take 1 hour and 49 minutes, and now it takes only 49 minutes. So the build system overhead that they had was more than 50%, 1 hour out of less than 2. And getting rid of these sorts of inefficiencies makes your life as a developer a lot nicer. And so the thing that defines Meson as a build system, which separates it from other ones that exist, is that we have a domain-specific language that's defined for defining your build. And it's actually quite close to Python. It's not in Python, so it could be you could re-implement it in a different programming language if you wanted to. But we stick fairly close to Python because it's actually pretty good. The syntax is really nice. So let's look at an example for a very simple project, which is compiling C source code and using a dependency. So first you define your project and give it a name and a list of languages that it's going to be using. So here we have a sample project and it's using C. And then we need a dependency called glib 2.0. And the system then goes out and looks up where is this system. On Linux, it will use package config, and on other systems, it uses other mechanisms to find this dependency, and it returns that. And then we define an executable called myprog in this case, which consists of one C file, and then we tell it that this particular executable is using the glib dependency. And then it takes care of putting all the linker flags and the compiler flags and all that sort of stuff, and just creates the executable. And then we create a test, which is just give it a name again, and then the executable that you want to run. You could specify like arguments to give and so on, but in this particular case, we don't care. We just need to run it and see if it returns 0, then everything is fine. So this is 4 lines of code, and even if you've never done like any sort of Meson programming before, it's fairly understandable. You can understand what's happening here, and there's nothing that's really extra. You don't have to care about is this, if I'm on Windows, do I need to put .exe on the file name and all those sorts of things? Because you don't really care, you just want things to work. So we take care of those. But to look a little bit deeper, if you think about a build system, so what does it actually do? Well, there are 3 different levels of where you can go. So let's start with the simple one. And this is pretty much 99% of what a build system does. So in the middle, you have your compiler and your linker, something like GCC or Clang or Visual Studio or the Intel compiler, and you feed it source code. And then there's external dependencies, which come from usually in the system, but they can come from anywhere else. And there's some compiler arguments that you want to give it, such as compiler defines and all that sort of thing. And then from that, you get some sort of output, which is usually a static library, a shared library, or an executable. And that's pretty much the whole gamut. And this, when you boil down to it, this is what it does. Okay, but let's look at the more advanced level. So slightly more advanced level is that you have 2-phase things. So first you build some sort of library, and then you create an executable that links to the library that you just built. So in this case, we have taken the dependency, which you can see from there, and we've actually built it ourselves. And this is just the advanced level, if you will. And then if we go one step further and we go to the expert level, then you get something like this, where you take source code and then you create an executable, and using that executable, this could be something like an IDL compiler or something, you generate new source code and then you compile that. And at its core, this is all the thing. I got this in the got this in the wrong order. So these are the primitives that you need to create a build system. That's basically all you need. Now, if you ever done anything with makefiles and all that, this is a lot complicated. And if you get into the really low level, it gets a bit complicated. But you as the developer, you really don't care that much. You just want stuff to happen. There are, every programming language has its very own special things that you need to do. Fortran has a very weird way of defining modules, so you need to do things. But basically, the core is pretty much the same. You just say, here are my source files, here are my dependencies, make stuff for me. So the way this usually is implemented, and the way, sorry about that. This usually works, is the same on pretty much all build systems that there exist. So first you read the build definition files, which tell you what sort of things need to happen. Then there are tests on the system. So usually you need to check something like what's the size of the pointer, or is there such and such header available, and all those sorts of things. You need to compile small tests to see what the system is like, so you get the results from that. So you need to run those. And then when you read the build definition file, what you build up is a graph of what the build looks like. And then the system needs to evaluate that and see how it's all built up. Then you serialize this graph out to a series of steps that need to be executed one after the other. And then you write this serialization in a backend format. This can be something like a Visual Studio project file, or a Ninja file, or a Make file, or Xcode project, or something like that. And then the final step in this is that then you just run the build. But if you changed the build definitions, then the system needs to detect that and regenerate itself to build the new description. So if you change the build definitions, it needs to automatically fix itself. So what this means in detail is that the things that a build system needs to do are string parsing and manipulation, reading files, parsing them, getting the output of executables, and all that sort of stuff. You need to be able to run external programs and parse the output that they produce. You need to be able to deal with graphs of moderate size. So 1,000 targets is it's a fairly big project for a build system, because you count the targets and not the number of files that are in it. And then you need to be able to do file manipulation in a cross-platform fashion. On Windows, you need to have the slashes the other way and all that sort of stuff. You need to be able to spawn processes in a cross-platform way. And if you have a dependency manager, then you need to download dependencies from the internet. So you need cross-platform network operations. And if you look at these things and like think about it for a while, these are all things that Python is really, really good at. It's kind of like a abstraction layer over operating systems. And because Python is so great at doing these things, then we can leverage that if you have a problem that fits exactly in this model. So let's look at how this actually pays out in practice. So there are a bunch of different systems, build systems available that you might be familiar with, and there's this service called openhub.net. And what they do is that they parse these different open source projects and they do different kinds of statistics and then allow you to look into those. And they have a list of like source lines of code for each project that you might be interested in. So let's look at some. So the traditional GNU auto tools is 23,000 lines of autoconf, which is its own language in the OpenHub specification. There's 87,000 lines of shell and 14,000 lines of Perl, which is a substantial amount, and none of these languages are what you might call developer-friendly. Another thing which is very popular and used quite a lot is CMake. And CMake is 900,000 lines of C++. That's almost 1 million lines of code to do these sorts of things. And they also have their own. CMake is a lot of that is written in the scripting language of their own design, which is what you also use to write your build definitions. And there are 200,000 lines of that. So there's more than 1 million lines of code. Now, this is all code, so it probably includes unit tests and all that sort of stuff. But it's still a fairly substantial amount of code. And another thing which is also quite popular nowadays is Google Bazel, which is the build system that they use to build their multi-million line, 250 million lines of code as of last reported number source code, and that's 600,000 lines of Java, and again 370,000 lines of C and C++. This is again, probably a fair amount of that is tests, but they're mostly in the C and C++ side. Java is probably the main implementation language. I haven't looked that deeply into it. So for comparison, Meson is about 25,000 lines of Python, and then there's 5,000 lines of C and C++, which are the unit tests. And, because there's no other language other than Python in the actual implementation. So if you compare 1 million to about 30,000, you have a ratio of 1 to 30, which is more than 1 order of magnitude. And if you have 1 order of magnitude size difference, it makes a huge difference when trying to understand what the code actually does. If you want to participate in a project that has 1 million lines of code, it's really hard to get a grasp on what you actually want to do. But if you have something like, which is 20,000, then it's a lot more feasible. It's something that if you put some effort into it, you can actually do with like not massive amounts of time and effort spent. So this means that it's easier to hack on, it's easier to contribute, and as a project, it's much easier to run because then you get a lot more people who are contributing into your thing. And this is the true power of Python, really, is that there are things which are extremely laborious and they're boring and they're not very nice, and Python makes all of that problem go away. Things become simple. You don't have to care about a lot of things. Sometimes you do, but you only need to care in the very few special cases and not everywhere all the time. And also, if you have good tools, if you have the right level of abstraction that fits your problem, then you can do great things. One of the most difficult things in problem solving and programming in general is to find the right abstraction level for the problem that you're trying to solve. And if you use the wrong level for the problem at hand, then you're not going to have a good time. You're going to like spend a lot of time reinventing stuff that you shouldn't really need to reinvent, or then just having your massive framework which you're trying to then smash your problem into pieces that you can control. But if you get a problem which is of a certain shape, and then you get a solution which you can get the exact same shape, then you can do a lot with very few, not a lot of effort put into it. The obvious follow-up question then is that would it make sense to rewrite in a different language? There are various reasons for this. The answer is a definite maybe. It might. The obvious reason why you might want to think about it is that there's a performance problem. But that's not actually it. So we've done a fair bit of benchmarking, and the things that are currently slowing us down are mostly nothing to do with Python. It's just like we need to call external programs to find out what the system state is, and you can't really make that faster, because if you execute an external program to do something, then you just have to wait for it to finish, and there's not much to do. But the actual big problem that there is that duck typing is awesome, but it only works up to a level, and then things get really difficult. We have a very good set of tests, so we can change things fairly freely, because things are going to be found in test if things are broken. But as you get much beyond 20,000 lines of code, then it gets difficult in a way that's hard to quantify. So having maybe typing module is something that's going to be useful in the future. But for the moment, once Python gets to a certain size, then you might want to think about splitting the problem in two, or implementing parts in some other language or something like that. Okay, so putting it all together now, let's create a Python extension module as an example. How many people here have tried to compile a Python extension module without setup tools? Nobody. With setup tools? Did you enjoy the experience? Okay, I see shaking of heads. Okay, so let's create a Python extension module, but we're going to use C, C++, Rust, and Fortran in the same module. So let's see how that would go. So the build definition file for this would look like the following. So if you search for Polysnake, you will find the GitHub repository where this is stored, so you can try it yourself. So we just say that we have a project, it's called Polysnake. It uses these languages. And then we import the Python. So this is the internal module system that we have. It's the Python tree is the module which contains helper functionality for creating Python modules. So we import that. And then there's the dependency Python tree. So this then goes to the system and finds all of the things that you need to have in order to build Python 3. So the package config on Windows, it uses because it's running in Python, you can query the running Python interpreter on how you should build modules for this particular interpreter and all that sort of stuff. Okay, so then we built a Rust static library. Rust is a bit special, so we have to build it on its own. And then we create a Python extension module, which has this name. And here are the source files that it contains. Oh, there's an extra comma there, but just ignore that. So there's the C file, CVP file, and the Fortran file. And then we link with the Rust library that we just built. And we say that it uses the Python 3 dependencies. And this is all you need to write. And it just builds the .so file, and you can just do things. So the thing is that simple things should be simple, and hopefully they are. And hard things are possible. You might need to do some work. but most importantly, life is too valuable to spend babysitting compiler flags. So, sorry. So, in conclusion, Python has traditionally not been used in the very lowest levels of a Linux operating system. Most of the tooling there has been done in the late 90s, early 2000s, and it's mostly been in Shell and possibly in Perl, so they haven't really used Python that much. But this is now changing, because now that core system libraries are built with Python, you really need to have that in the core layer. And once it's there, it's probably going to start replacing all of the old and gnarly bits that are there. And this is the main thing, is that if you have, if you can take the strengths that Python has, and if you use them efficiently, you can achieve roughly the same functionality as in other languages with 1/10 of lines of code in it. Building source code, because of these things, has now gotten a lot easier. So I've gotten people like tell me, it's like using the word love to tell me how they like their build system, which is like, I don't think it's been said much in public at least. And really ultimately is that simplicity is power. And this has been my presentation, and if there are questions, I'll be happy to take them.
Thank you very much for the presentation. One question from me. Maybe I have missed this, but which large projects, or maybe what's the number of projects that already use this build system? Do you know?
Yes. Oh, actually, it's so the slide is there.
Okay.
Thank you for the amazing talk. That was very interesting. I have a question that what are the bad cases of Mesos? What are the cases when I don't want to use Mesos? What are the drawbacks, bad stuff?
Okay, so currently, if you have something that's 100 million lines of code, then that's untested. We don't know if that actually works.
You mean very big or?
Very big projects. Another thing is that if you want to build everything from source yourself, and you want to have like a unified build definition, then we don't have the build definitions for all of the dependencies. So this, if you have written them in your existing one, that might be a reason. Our Xcode project generator is not particularly great. So if Xcode is like a tier 1 thing for you, and you actually want to use the IDE itself, then that might not be the best possible case. But if you just like use Ninja to compile on OS 10, it works quite fine.
Yeah, thank you. And another question: this Mesos is Apache Foundation thing, right? Or am I wrong?
Mesos is, Meson isn't.
Yeah. Okay. Sorry.
That's a container thing, I think.
Yeah. Okay.
Any more questions?
What about dependencies on Linux? If we have not package config for dependency, is there a problem or not?
It works out of the box.
And we can build off a dependency from source code, like we can with CMake, for example.
Yes. So, where did I put the example code? Okay, but you remember that you had the example code where it says dependency glib?
Yeah.
So that, by default, it goes out to the system and it builds, uses package config to find dependencies. But you can also say that, so in Meson you can take any project and build it as a sub-project transparently inside your thing. And then you can just say, no, instead of the system, actually what I want to do is that I want to have it from there where I build it myself. and your build definition stays the same. The dependency just carries the information that this is actually an internal dependency and not an external one. And as an example, so the GStreamer framework, which has hundreds of plugins and so on, it's actually divided into 3 parts or more parts. And but you can build all of them in one clump using this sub-project thing, where they build and they just use themselves as opposed to using the system one. And also, if you're on Windows or OS 10 or somewhere where the system dependencies are not available, then it just builds it as part of your project.
Okay, thank you. And now one question about some install functionality, like we have in CMake. It may be useful from time to time. Does it have?
Yes. So we support all of the default install things that are when you need to install on Unix. So prefix, USR, and all that sort of thing. And we do all the symlinks for the SO files and all that stuff, and it just works.
Thank you.
Hello, thank you for the speech. Could you please, is it possible to open the definition of the project, where you define its name and saying what languages it uses? Yeah, okay. As I understand, this sample project uses C language, so it automatically finds the interpreter and, I don't know, GCC or something, right? Yes. So is it possible to, I don't know, to define, I don't know, if I want Python project and say that I want Python 2.7 or Python 3.6, is it possible to define the version I want to use in that project?
So Python is a bit special because you don't really need Python to compile. You can just run it and give it the source codes and it does all the things by itself. But if you want to compile like a C extension, then you can, when you run Meson for the first time, it's always builds out of tree. So you need to have a build directory. And when you define your build directory, well, you also need to define what compiler to use. So that would usually be GCC or the system compiler. But you can have as many build directories as you want, and you can just set up them to use different compilers. If you want to build with GCC and Clang and different versions of Clang at the same time, you can just have a build directory for each and then just choose which one to build.
So it's done automatically, or it should be done myself when I define the configuration for it?
So we do the default, so the same way that CMake and AutoTools and all the other ones work, is that when you run it for the first time, we see the CC environment variable and CXX and just use that one. And if they're not set, then we do the auto detect.
Okay, so and if I want to define my own, I know compiler, I know JavaScript or something that I want to run, is it possible to do?
So if you want to support a completely new compiler, then you need to submit it upstream. It needs to be changed in the source code. You can't define, because we need to understand how to use the compiler, then it really needs to be inside inside the Meson.
It should be some kind of extension to the Meson?
We don't really allow extensions. We want people to submit their things upstream, so we have one place where all of them are maintained.
So if I want to add another compiler, I should just create a pull request to the...
Yes.
Okay, thank you.
Yeah. So currently we have Intel compiler, Visual Studio, Clang, GCC, and I'm not sure of others. Some people have wanted to put Mscripten on, and a bunch of other ones, but we haven't heard from them.
Okay, thank you.
Okay, just a bunch of questions. Actually, first of all, this is the tool on the same level as CMake, so it
yes.
So makefile may be output of this, or it can work without makefile.
So we generate Ninja files, and we don't support make, and we will never support make, because Ninja does everything that make does, but it does it a lot better.
Okay. As a few more questions. What about cross-compiling? Does it support cross-compiling out of the box?
Yes, and supports cross-compilation for bare metal targets or Windows or iPhone or Android and all that stuff.
Okay, you showed it on the example of Debian package, so it's integrated with Debian helper in some way.
I think so, yes.
Okay.
Hello. Can you tell more about the syntax of this config file? Is it extension of regular Python syntax, or it's a completely new language?
It's a completely new language. It's defined only for this. And the main thing about this is that this is not Turing complete. And we have specifically chosen it not to be, because then you can create tooling to manipulate it. And it's a lot simpler. And like writing your own functions inside your build definitions is not like, it's not really something you should do. It's just like, this is what I want to happen, and then we take care of the rest.
Okay, thanks.
Can you tell a bit more about extending the Meson build system? For example, if you have a large project, there are often a lot of domain-specific patterns in the build definition files, something like, this is a component of my very big system, and it applies a lot of configuration, common configuration that developers adding new components should not care about. And usually you write functions for this kind of extensibility in the build system. If you say that Meson doesn't support functions, what about this use case?
Okay. So you're thinking about something like you build some sort of shared library, and then you want to use it somewhere else, and you need to have the include files and flags and what to link with, something like that.
Not exactly. For example, if there are several hundred plugins in plugin build targets in a big system, and there is a rule that there should be a definition, plugin name, something in all of them, and a developer adding new plugin should not care about that, and it should be defined in a central place, this rule.
Okay. So when you compile these plugins, do they need something special besides compiler flags and something so like, or what sort of things do they need?
Yes, there is some pattern, some configuration pattern that is common for that should not be repeated in 100 places in the build system.
Okay. So there are many different aspects of this problem, and we'll probably talk about this later outside. But one core that we have is that you have the dependency, like here, you have the dependency. So you can define an internal dependency yourself that looks like exactly the same. So then you would say shared module, that's your source file, and then the dependency that you defined elsewhere, and then you wouldn't have to do anything else. If you need to do something more complicated than that, then you probably need to look into it case by case basis. So we specifically try to keep the build definition language as minimal as possible, because if you allow people to do something, then you're going to find that they start spawning threads and do all sorts of things, and it's just things fall apart.
Thank you.
Okay. Last question from me. Very fast. Do you support Cython?
Yes. Yes. So
Good.
there's out of the box. So
Good.
so the way we write our unit tests, actually kind of like example projects of how you would use it. And if you're interested in that, there's a Cython test with that gets run, and you can just copy stuff from there.
Okay. So let's thank the speaker again. And now it's time for the coffee break.